This is Physics 102B, Chapter 15 homework, Part 1. We'll start with number 29. Here we have 1 kilogram of carbon. One thing you have to know is that carbon has an atomic weight of 12. That's useful because we need to know how many carbon atoms we're dealing with. So starting with 1 kilogram, we divide by, let's say 1,000 grams. We can divide by 12 grams per mole. That's what the atomic weight tells us. That will give us the number of moles that we're dealing with, multiplied by Avogadro's number. This will give us how many atoms of carbon we're dealing with. Then you have to recognize that carbon is atomic number 6, meaning it has 6 protons. So if it's neutral, it's going to have 6 electrons to balance out those 6 protons. So we multiply by 6 electrons per atom. And we get 3 times 10 to the 26th electrons. Number 32, if a net negative charge is gained, that tells us that electrons were gained, so there's a mass increase because electrons were gained. So we take the charge that was gained, negative 2.3 times 10 to the negative 8 coulombs, divide by the charge per coulomb, the charge in coulombs per electron, and that gives us a total of 1.44 times 10 to the 11th electrons that were gained. Then we multiply by the mass of an electron to give us our answer. Next, number 33. Number 33 involves a force at a particular distance, that's F0 and R0, and now the new electrical force at a new distance. And a technique that we've done several times in class is we start with the Coulomb's law and arrange it so that all the varying quantities are on the left-hand side and all the constants are on the right-hand side. So we get F times R squared equals K Q1 Q2, but we'll just call that right-hand side constant. So we recognize that F times R squared is constant. So we can say F1 R1 squared equals F0 R0 squared. Then we solve for R1 algebraically. We get R1 equals the square root of F0 over F1 times R0. Plug in the values, and we get a new radius of 0.38 meters for the distance between them. Next is number 37. Number 37 involves 2 ping pong balls. The one on the bottom of my diagram is fixed in position. The one on the top is levitating. And there you see I've drawn a free body diagram of the one on top. It's got the electrical force of repulsion pushing it up and its weight pulling it down. And you could skip right to this step and just say that those forces balance. But remember, that's based on, from first semester, F equals ma. Electrical force up minus weight going down equals 0. Or you could have just skipped to this and showed that those forces are balanced. When you take this equation and solve for r, you should get r equals square root of k q squared over mg. Plug in all those values, and you get a distance of 0.364 meters. Next, number 42. Number 42 says find the net force on each charge. So what I've done, you can see my diagram at the top of the screen there. And what I've done below the x-axis is to draw which way the forces are going. So this is the force diagram on charge 1. It's got the force from charge 2 pushing it to the left, the force from charge 3 pushing it to the right. Charge 2 has both forces pushing it to the right because charge 1 is going to repel it, charge 3 is going to attract it. Charge 3 has both forces going to the left because it's attracted by both 1 and 2. So now let's find the magnitudes of those charges, or of those forces. Starting with the force between 1 and 2. Just apply Coulomb's law, and you get 21.6 newtons. The force between 1 and 3, you get 1.8 newtons. And the force between 2 and 3, you get 10.8 newtons when you plug in for Coulomb's law. Now, you go back to the diagrams and recognize that the force on charge 1 is going to be, we're going to do, if a force was pulling to the right, we'll call it positive, to the left, we'll call it negative. So the force on charge 1 was the force between 1 and 3 minus the force between 2 and 1, and that's going to be 1.8 newtons minus 21.6 newtons for a total of 19.8 newtons to the left. Or in vector notation, I have negative 19.8 newtons I hat. The force on 2, it's the addition of both the forces F21 plus F23, and that's going to be 32.4 newtons to the right. And finally, the force on charge 3, I'm subtracting them both because they were both pulling to the left, and it's going to be negative 12.6 newtons I hat, or 12.6 newtons to the left. You might also notice that if you take each of those three answers in vector notation, you add them up, and they add up to 0. Just an interesting product of internally the total forces between them is 0. Okay, number 43. Okay, here we go. Number 43 has 2-point charges, 1 meter apart. Where should a third charge be so that the net force on it is 0? Well, one thing you can think about is what region should our charge be? It could be possibly to the left of the 25 microcoulomb, it could be in the middle somewhere, or it could be to the right. But since both these are negative, think about if we put a charge to the left, depending on its charge, let's say it's positive, it's going to be attracted by both of those charges. If it's negative, it's going to be repelled by both of them. So there's no way that's going to cancel out. And the same thing would happen if it were on the right. The only way the forces are going to cancel out is if the charge is somewhere in between them, so that it'll either be attracted by both or repelled by both. So we know it's got to be in this middle region. We're going to find where that position is so that both those forces are equal, meaning they'll cancel each other out. So the way we need an expression for its position or its distance, and let's say that x is its distance from the 25 microcoulomb, and 1 meter minus x is then going to be the distance from the 75 microcoulomb. I set the forces equal to each other, and then you plug in Coulomb's law. Both of those terms on the left and right have a common feature. They both have k and they both have q, common factors. So we can divide away k and q, and you get what you see on the bottom of your screen. with the negative 25 microcoulombs and the negative 75 microcoulombs. Now, one more thing we can divide out. Let's divide both sides of that equation by negative 25 microcoulombs. Then we're left with just, right here, 1 over x squared equals 3 over 1 minus x squared. And the rest is algebra. At the bottom of the screen, you have two solutions. You could expect that because it's a quadratic equation. But the negative answer would be in the region that's to the left of the negative 25 microcoulombs. And we already decided at the very beginning of the problem that that region is no good. So we go with the positive answer, which is 0.366 meters from the smaller charge. Number 47. It asks for what is the charge on, what is the force on each of the charges, but it's very helpful, and it'll cut down about 75% of the work we'd otherwise do, to recognize that there is symmetry in this problem. Because they're all the same charges, it's all around a square, they're all the same distances. No matter what charge we compute for, the answer is going to be the same. So I've labeled these charges around the square 1, 2, 3, 4, and as I'm doing the problem, I'm going to solve for what is the net force on that charge number 1 that's on the upper right hand. And the first thing to do is to solve for what are the different forces. Now, force from 2 and force from 4 acting on 1 are going to be the same. K times q squared divided by the x, the length of the square. The force from charge 3 is going to be different. You're dealing with the diagonal of the square, so the distance is actually square root of 2x. When you square that, you end up with kq squared divided by 2x squared, which you'll notice is 1/2 of the force from 1 to, or the force between 1 and 4. When I draw a free body diagram, because we're going to have to break this up into its vectors, on charge 1, we have the force 1, 2 pushing it up, the force 1, 4 pushing it to the right, and force 1, 3 pushing it at a 45-degree angle. Now, from that free body diagram, we have to break it down into the vector components. So we have the sum of the x components is force of 1, 4. That should really be force of 1, 4 times the cosine of 0 degrees, but that just becomes 1, plus force of 1, 3 times the cosine of 45 degrees. So what I've done, I wanted to just save ink here. This part, is the force from 1, 4. And what I left off was the second part, the force of 1, 3 times cosine 45. Here I actually solve for these numbers. So this part right here, this component, is the force from 1, 4. It's 4.516 micronewtons. Plus, and remember force from 1, 3 is going to be half of that, and then times the cosine of 45 degrees. So you should get 6.11 micronewtons. When you do the y components, you should see that it comes out to the same. The sum of the y components also gives 6.11 micronewtons. So that the final diagram I have here is that the sum of the x components is 6.11 micronewtons, the sum of the y components is 6.11 micronewtons, and so that gives a hypotenuse. The net force is 8.6 micronewtons at a 45-degree angle. So then what we have is that charge 1 is being pushed away from the center of the square with a force of 8.6 micronewtons. And because of the symmetry of the problem, we can also say that all of the charges are being pushed away with a force of 8.6 micronewtons.